So in this lesson, we're going to finish up with the pressure effects from a nuclear detonation. So we've looked at atmospheric, we've looked at underground, and now we're going to look at underwater effects. Now we can classify underwater detonations kind of in two categories. The first category is going to be what's called a shallow burst, and it's generally something within 200-ish feet of the surface of the water. And sometimes the depth, the entire depth of the body of water is also fairly shallow. So what this means is our detonation is going to interact not only with the air-water interface, but also the water-ground interface at the bottom of the body of water. The second type of nuclear underwater detonation that we're going to look at is something called a deep water burst. Now, deep water burst, the name sort of implies, is fairly deep under the surface of the water, thousands of feet, and usually also very much thousands of feet above the bottom of the water. So what we end up with is basically we don't see a lot of interaction with the air water interface, nor do we see a lot of interaction with the water ground interface. So let's start off by looking at shallow water bursts. And the one that I have up here is the Baker shot in 1946, a 23 kiloton detonation, which was only 90 feet below the surface of the water. And then we have the Wigwam shot, which was a little bit bigger, 30 kilotons, but 2,000 feet under the water, so much, much deeper. And they produce very different effects that we can see at the surface of the water, but also how pressure is transmitted through the water itself, underwater. So let's look at surface bursts. So with a shallow burst, depending on how close the detonation is to the surface of the water, we may or may not see a fireball. The fireball is basically that hot, heated, dense plasma that we've produced with that temperature and pressure from our initial weapon detonation. It can rise to the surface and actually break free, so you do see an actual fireball. But the deeper you go, the less likely this is to occur. Here's the reason why. When we have any kind of underwater detonation, we're creating a cavity very similar to what we do with an underground. Now, because it's water, we generally don't refer to it as a cavity. We call it a bubble, right? So we have all this high temperature, high pressure. We breach the weapon case, and now all of this is going to interact, again, very much like an underground detonation, with the material, in this case water, that's immediately surrounding the weapon. Now we're going to get ionization as this thing spreads out and starts to lose energy. So we're going to start with creating plasma, and then as the amount of energy and the temperature starts decreasing, then we're going to be vaporizing the water. And then as we move past that stage and further away from the center of detonation, then we're going to see something like we see with an atmospheric burst, where we're going to create a pressure wave in the water, and that's going to start traveling away from our detonation point. So we've now have a bubble or cavity of really hot mixture of gas. Oxygen stripped from hydrogen. So we have monatomic gases. We also have vaporized water. It's not, it's just vapor H2O. And then we have all the fission fragments and the remaining stuff from the weapon detonation itself. And this is at a very high pressure still. So it's going to want to move upward to seek out a much lower pressure area. Okay, so that's kind of what we've done for either a deep water or a shallow water burst. Now, as this bubble moves upward through the water, it's going to be constantly losing or radiating heat, transferring it to the surrounding water that it's passing through. So as we keep moving heat from our rising bubble to the surrounding water, the temperature is going to start getting lower and lower, depending on how close it is to the surface, how long it has during its ascent to lose that heat. If it's sufficiently deep, there will be no fireball, right? Because all of that, luminous plasma is going to, disappear as that cavity temperature, that bubble temperature, decreases on its way up to the surface. So you can have a fireball, but not necessarily. Again, it depends on what was the depth of burst. So I said shallow is considered less than 200 feet below the surface of the water. The fireball, if we do see one, is generally speaking going to be smaller than a comparable yield weapon in an atmospheric burst. And we're going to have something called a spray dome or a Wilson cloud that we'll talk about. And that's created at the base here. And it will very rapidly expand to create sort of a semi-spherical or hemispherical dome, if you will, that kind of encases and hides from view everything that's going on for a little bit. Very much like the pressure wave in an atmospheric detonation hides what's going on in the inner fireball. This spray dome or Wilson cloud is going to obscure for some amount of time, in a shallow water burst anyway, what's going on in the middle, where that big bubble of hot ionized gas and plasma and whatever is moving towards the surface. So one last thing, and I'll show you a picture of this later, is something called the slick. Now this is basically and also I think it's also referred to as the crack. And so this is basically that underwater pressure wave that we've generated from our point of detonation moving outward, interacting with the surface of the water as it races ahead of everything. And it basically just smooths the water out so that it looks very, very smooth, or it looks like a slick is what they referred to it back in ye olden days. Okay, now this is at a bit of a later time than what we saw with that initial fireball coming up out of the water before the spray dome had a chance to continue upward and expand. Here we see that the Wilson cloud has expanded to quite a large extent. Now, you might be asking, well, how come this water vapor cloud looking thing, how is this even formed? Well, it has to do with the pressure wave interacting with the water air interface. So just like with a ground detonation, underground detonation, we get that reflected tension wave, but we get an outgoing now pressure wave in the atmosphere. As we saw with a normal atmospheric detonation, that we have whatever that pressure wave is, it's at some overpressure. As it moves out, it's pushing all the air in front of it, so we end up with a low pressure regime behind it. And this low pressure regime basically allows the water to go from a liquid state into this vapor state, because as you lower the pressure, the ability of water to phase change becomes a lot easier. And basically that's what's happening here. And this is what that dome is. So this thing is following the outward expansion of our pressure wave, and it's just creating an area of mist. It will eventually go away. As it expands further, the pressure will start to equalize, and then the water will go back into liquid state instead of vapor state. So we can see this right here, this perfectly circular, smooth-looking water that it looks like it has its own vapor mixed in with it. This is sort of related to the slick. It's called the crack. And it is an interaction with the underwater pressure wave and the surface of the water as it races out in front of the detonation. Right here up at the top, we're going to look at this here in a second. This is basically a huge column of water that has been pulled up as the giant bubble of hot gas breaches the surface of the water and then rises up into the atmosphere. When it does this, it pulls a lot of, depending on again how deep the burst was, it can pull a massive amount of water up with it, and that's what we're seeing here. And it pulls up, and then eventually it's all going to come back down. So here we can see after the mist dome, the Wilson cloud has dissipated or is not present. What we can see is a giant cloud that's formed up at the top of that big giant column of water that we pulled up. We can see the column of water itself. But also what we can see here is what looks like this huge thing at the base of the column. Well, this huge thing is basically a giant wall of water that's now racing away from the periphery of the column, and it's caused by all of that water that we pulled up dumping back down and creating a giant wave called a base surge. Now, this base surge, we're going to look at it in a little more detail and give you some numbers that are associated with it. Now, this base surge is what does the primary damage to any surface ships that might be in the area, because it essentially like a mini tsunami. So you have something that's possibly 200 feet high, moving at a couple hundred feet per second. So that's a huge amount of mass traveling very quickly. So there's a lot of energy contained in that wave, and it slams into ships and it can capsize them. It can rupture the hulls, break them in half. And we did see this from the tests that were conducted very early on in the US's nuclear program. So let's look at it from a more diagrammic point of view. So this is what occurs after our detonation has breached the bomb casing, after we've created our hot bubble of gas and plasma, and after that initial pressure wave has raced radially away from our point of detonation. This picks up after that big hot bubble of gas and plasma, depending again how deep it is, after it's already breached the surface of the water and pulled a giant column of water with it. So we end up with basically a hollow tube whose walls are constructed of just basically water. Okay, so we will see a little bit of a depression in the middle of that column, because we're pulling water up, so the level of the water right in the middle of it's going to be down because it's basically coming like this. We have our pressure wave, which is racing outward, again, from our initial point of detonation. We have our air blast wave that is also moving outward, very similar to what we saw in an underground detonation. That upward moving pressure wave in the water interfaces with the air. We get a tension wave moving downward, but we also get a positive pressure wave moving out through the atmosphere. And then, of course, we have that condensation caused by the low pressure, so that because we have lower pressure, water can phase change easier, and that's where we get that Wilson cloud. This is about 2 seconds after detonation for a 100 kiloton yield weapon. So again, higher and low yields also change the intensity or the effects of what's going to happen in a shallow water burst. Bigger detonation, higher pressure values, a large volume of hot gas, which is rising to the surface, which can pull up more water, pull it up higher, and so on and so forth. But so 100 kilotons here. Now, if we look at 12 seconds after the detonation, that one was 2 seconds. At 12 seconds, that mist dome, because our pressure is kind of equalized in that area, our mist dome is gone away. The water has gone back into liquid form. And what we can see now is that giant column of water and the, basically a cloud of water vapor above it has started to fall back down into the body of water. So now you have a tremendous mass of water, again, coming straight down. It's going to hit and create a giant wave, okay? And that's the base surge, as I mentioned previously. So what we see here is that for 100 kilotons, the diameter of this water column that we've created is about 3,300 feet. So, more than half a mile. Actually, more like 2/3 of a mile. the amount of water that's being dumped and creating this giant wave creates that base surge, and the base surge is pretty enormous. It's got a primary wave height, so that first giant dumping of water creates a primary wave, a first wave, that's about 176 feet high, moving at about 200 feet per second. So imagine that huge mass of water moving that quickly and a wave that high. And it must have been a terrifying sight to behold if you could see it without, of course, being crushed by it. Now, if we move a little further on, water continues to drain out of that vertical column. So basically, we're creating multiple waves as it keeps dropping. So we see the first mass hits, creates that primary base surge. Then we see more of it hits, creates a secondary wave, and so on and so forth. So what we end up with is multiple waves moving away from the detonation site. So here we see at 20 seconds, we have another sort of base surge that's forming. It's a bit smaller than the initial one, but that primary wave, as it's moved away from the detonation point, has lost energy, so it's reduced in height and in velocity, going from 170 feet down to about 100 foot, and going from 200 feet per second down to about 100 feet per second. But we see a very similar wave forming right behind it. And we can see that right here, where we have the initial primary wave, and then we have a secondary wave that's been created again by more water falling out of the column, and it's moving right along with the initial base surge. Additionally, at this particular point, we are now going to see water precipitating out of that cloud that we've created by the interaction of that. Remember that big hot gas bubble? So we have a whole bunch of vaporized water that came up with it. As the temperature cools, that water starts to condense, and then it starts to come out as rain. Now, unfortunately, it's not just water at this point. It's bringing out all of that radioactive material that we have created via the fission process in our weapon. So it's very, very radioactive, and this poses a gigantic health hazard, as one might imagine. Looking even further out, basically what we're going to see here is that we're seeing the last bit of the base surge. So maybe another wave or two that's as the very last of that column drains out. We see that the primary base surge has lost even more energy. It's gone down to about 42 feet. It's only moving at about 75 feet per second. But most of the water is now gone from the column, and what we're looking at is that huge cloud that formed at the top of the column. It's now going to be affected by whatever the atmospheric conditions are, mostly wind. So wind is going to push the cloud in some direction or another. If there is wind, it's going to continue to precipitate out that radioactive water. So we're still getting that rainy fallout, if you will. But we're going to see another effect. If there is wind, depending on the way that the wind direction is facing, you're going to see, imagine that the wind is going here on this particular slide from left to right. So we have expansion going on in all directions from the base surge. What you're going to see is where the wind is opposing that motion, it's going to basically retard the motion of the water as it moves in that direction. So we're going to see it lose even more energy. Waves are going to get smaller. They're going to move slower. However, on the opposite side, the wind's going to help everything move. And that's all that this is showing. This is what carried by surface wind diagram here. Okay, so finally what you end up having is a series of waves. The wave heights are very much lower than that initial base surge. They're down to a very manageable 18 feet. Pretty good for surfing. They're also not moving very fast, only about 30 feet per second. You have that primary cloud still producing radioactive rain. But what we end up seeing is a secondary cloud forms in between the surface of the water and that very upper cloud. And this is basically caused by the base surge itself, and what it's actually precipitating out is just kind of normal water. It's not really radioactive like it is coming up from the top. So now we have a series of waves that were created as that water column continuously emptied. The amount of energy that was contained within those waves has been dissipating as it moves spherically outward, up until we have a series of waves that aren't very high at all, not moving all that fast. And then we have two sets of clouds, one that's producing radioactive rain and one that isn't. So let's see. I have some notes that go with this. I want to just check them out here real quick. No, that's fine. One additional thing, not only are, when we pull up that big bubble of hot gas and plasma and radioactive material, depending on how shallow the body of water was or how close the detonation was to the seafloor, when the pressure wave, that primary pressure wave interacts with the seafloor, it reflects back up. Now, because we're going from less dense to more dense, we're basically just reflecting that pressure wave. It's not a tension wave. When that happens, it can pull up material from the bottom of the body of water, and that can get all mixed in with the radioactive material and the hot gases and stuff as it ascends and breaks the surface. So we can have even more junk that will precipitate out of that top cloud. And this is just a nice clear diagram of what happens for a shallow water burst, where interactions are happening both with the air-water interface, but also with the water-ground interface. As with an underground burst, we're going to see at the surface of the water-air interface, we're going to see the creation of an outward moving pressure wave in the air, but also a reflected tension wave moving back downward towards the point of detonation. And then, as I mentioned just a second ago, when it interacts with the ground underneath the water, it's not going to produce a tension wave, but it's going to produce a reflected pressure wave, very much like we saw with an atmospheric detonation close to the ground. So we have our triple points. We don't really get a Mach stem underwater. And we can see our transmitted air shock and our transmitted ground shock. And just like with an underground burst, that transmitted air shock interacting with the surface of the water, also called air slap. Now, deep water burst is a bit different. Okay, so the main thing with a deep water burst is, again, we create a cavity of hot gases and plasma. But as it moves upward through the water, it's constantly getting heat, energy removed from it. And as this happens, eventually we have no plasma, so no luminous fireball. And then we end up starting to get some condensation as well. So some of the, towards the outsides of this bubble as it rises, so some of the water vapor turns back into water. Again, the temperature starts cooling down by an incredible degree. And so when this thing finally the bubble does hit the surface, it's also not moving much very fast anymore, because, again, as we lose temperature, pressure starts lowering, so it rises. So it rises a bit slower. And what we end up seeing is just kind of like a little small geyser of water as that bubble breaches the surface and pulls some water with it. But it's very brief. It doesn't last very long. And it really doesn't leave anything afterwards. So you really can't see any kind of real after effects at the surface of water from a very deep burst. And that's just what this shows. Here's the gas breaching the surface, pulling the water with it. Here's the water going up and then starting to come back down. And then eventually all you have is basically a curtain of a combination of water and water vapor at the surface, which will then pretty quickly disperse. So underwater geometry. There's really only one thing that we're going to be all that concerned about, and that is this slant range from the explosion to whatever target that we're concerned with. We're also kind of concerned with the depth of burst, so that we know what regime that we're in. Now there's these two other R's, so ranges. One is the range of the reflected surface wave, which comes up and then back down. And then, of course, we have the range of the reflected bottom wave right here. Then we have, of course, depth of water and the horizontal range between the detonation and whatever target we're looking at. We're mostly going to be concerned, for all intents and purposes here, with that slant range. And we can calculate the slant range if, as we did with, with the atmospheric burst, if we're given the, the appropriate corresponding value so that we can draw a triangle and do a little bit of math. So before we sort of finish with this section, let's take a look at what, I said that when we interact with the surface in a shallow water burst, we get the outgoing air pressure wave, right? We displace a bunch of water, compresses the air, we get a pressure wave moving out, but we also get a reflected tension wave. Now if we look as a function of time, we end up looking at this pressure interaction with the tension wave and the outgoing pressure wave of the water. Now, if you look in time and looking at that pressure wave as it expands outward, the underwater pressure wave, you'll see that it starts at a very high pressure and gradually, as it expands, it loses pressure. Now, here comes the interesting part. When we get the interaction with the pressure wave with that reflected tension wave, so you can think of the pressure wave as being positive and the tension wave as being negative. So what can happen is we can get different cutoffs for that pressure wave as a function of time and also of distance. So what we can get is a partial cutoff of that outgoing pressure wave in the water, and that's where the reflected or the tension wave isn't low enough to completely bring the pressure of the outgoing wave down to normal. So as we can see here, it's a little bit less, but it's still decreasing. So what it does is when that tension wave interacts with the primary outgoing pressure wave, it can lower the total amount of that pressure. And so it reduces it, so it drops off a little bit faster than it would be had there been no tension wave. Then we have, if the tension wave is actually quite large, and when we add that negative to the positive pressure wave, we end up with something that's actually lower than normal pressure in the water. And so we see that if this dotted line represents, of course, normal pressure, we see that if we have a pretty powerful tension wave interacting with our initial outgoing pressure wave, we can get pressures resulting that are lower than whatever the normal pressure is at that particular depth. And then finally, we have something right here, which is called cavitation limited. And this, if you're not familiar with the phenomenon of cavitation, it's basically that you're turning water into vapor. You're reducing the density. And this can happen from, with boat propellers accelerating the water too much, putting too much energy into the water, we can end up producing air pockets or gaseous pockets and causing some issues. But if we have too much of that negative tension wave that reduces the density of water below the vapor pressure, we'll end up producing a lot of air or a lot of cavitation, and that's going to halt it altogether. So we can have our pressure wave, tension wave interaction result in a lessening of our pressure wave, but it stays above nominal. We can have it drop below nominal and then slowly increase back up. Or we can have it hit the point where it's below the vapor pressure of the water so that we're producing water gas ultimately. And then once that density has severely decreased like that, the pressure wave can't really travel anymore. And that limits the time or distance duration of that underground pressure or that underwater pressure wave. All right, so let's look at deep water burst. So here's a peak overpressure figure for a underwater burst. And it gives us peak shock pressure and PSI on the vertical axis. And of course, it gives us the slant range in thousands of yards. Very important to remember that, thousands of yards on the x-axis. Now, this is log scale. So we have 1 kiloton all the way up to 1 megaton. If you were to have, say, a 5 kiloton blast, the spacing between these two lines, you wouldn't divide it up into equal segments. You would have to divide it on a log scale. And if you're curious how to do that, just let me know, and I can sort that out for you. It's not super difficult, but it is something to keep in mind if you're going to try to interpolate off of a log figure. You'll notice there's no scaling at all here. We have different lines representing different yields. This is out of Glasstone and Dolan, and this is basically giving this the same thing, but a bit more comprehensive with the yields of the weapons. We have 1 kiloton, 5, 10, 20, so on, all the way up to 50 megatons. We have scaled slant range thing here in the corner. Don't worry about that. You won't be needing it. You'll just be reading off here. So slant range to find out for a particular weapon yield, what is the peak shock pressure. Okay, so wave arrival. Okay, now wave arrival is based off of, hold on, let me, I think I did this out of order. Yeah, okay, so let's go to the next one. There's something called a time constant, and this time constant is based off of the size of the detonation and how far you are away from the target, or the slant range. So again, we figure out our slant range. We can look here based on the yield of our weapon, and we can find something called a time constant. And this gives it in milliseconds. Also important to remember, it's milliseconds. Now, once we have this time constant, then we can come back to this one and look up something pretty cool. Now, if you remember with the atmospheric detonation, we had that one graph that had two different curves on it. One gave us instantaneous power at some point in time, and the other curve gave us the cumulative power at that particular point in time. Well, this is very similar. And what we're looking at here is we can take a particular point in time, t, and we'll divide it by that time constant that we looked up on the other figure. Okay, so say that t over the time constant for whatever we're using, doesn't really need to be anything special. Let me get my pen working. All right, let's say it comes out to be 3. So we're going to look right here. Then we're going to come over here to this axis, and we're going to draw a very not straight line, but sure, it works for me. And we're going to read the value off here. This is going to be 0.09. Okay, and that's going to be our reduced shockwave pressure at that time we chose. So in order to find out what that pressure actually is, we're going to take that 0.09 and we're going to multiply it by that peak overpressure. And we'll get the instantaneous pressure at that particular moment in time. Again, this is just what we did with the atmospheric detonations. Okay, wow, black screen. So that's going to be it. This is pretty much the end of the pressure portion of the nuclear weapon effects. The next thing we're going to be looking at is the effects of radiation, both prompt and residual.